Welcome back to The Explainer. Today, we're taking some seriously complex ideas and breaking them down visually to look at the fundamental logic of how software is actually built. If you're a student coder, or honestly just someone who stared at a massive piece of software and wondered how human beings coordinate that staggering amount of code without totally losing their minds, well, you're in exactly the right place. We are going to explore problem specifications, abstraction, and decomposition. And hey, think of these not just as fancy vocabulary words, but as your absolute literal survival tools for coding. Let's kick things off with a massive challenge that instantly highlights why we need a structured way of thinking. Seriously, how do you build a complex video game from scratch without getting completely overwhelmed? Think about the sheer terror a new coder feels when looking at a sprawling game like Minecraft or Breath of the Wild. I mean, the endless mechanics, the complex physics, the thousands of interacting items, it kind of seems like pure magic, right? But here's the secret. Great games aren't born from some chaotic spark of genius. They're built from rigorous, repeatable, fundamental logic that literally anyone can learn. To get there, here's our roadmap for today. We're going to hit 5 key areas. First, the computational mindset. Then, abstraction, followed by decomposition. After that, we'll dive into a case study on game development, and finally, putting it all together. All right, let's jump right into part 1, the computational mindset. So before you write a single line of code, you absolutely have to construct what's called a problem specification. This basically defines the boundaries of your goal. You need a clear problem statement, you've got to outline your constraints and limitations, define your high-level objectives, and, this is absolutely crucial, detail your input and output specifications. Why does this matter? Well, imagine you're building a small game feature, like a jump mechanic. If you don't define the constraints like gravity, the inputs, say hitting the spacebar, and the outputs like upward movement on the y-axis, you simply can't write an effective program. You just have to know exactly what you're taking in and what you're expected to produce. Now to actually start solving that specified problem, you're going to need the first superpower of computational thinking, abstraction. This is the process of simplifying a really complex system into an easy-to-use interface by basically hiding all those messy, unnecessary mechanical details. It lets us focus entirely on the problem at hand without getting completely bogged down by everything churning in the background. Think about the massive relief this brings. Abstraction is exactly what lets a new student use a game engine's built-in physics system to make an object fall, without needing, a PhD in calculus to program the real-world mathematical laws of gravity from scratch. Okay, next up, we have algorithmic design. This is the actual step-by-step logic and the rules the system is going to follow. Once we've abstracted away all the irrelevant details, we need to outline the specific, super precise conditions under which actions occur. In a game, this means defining the exact sequence of events when, say, a player hits an obstacle. For example, if the player's virtual hitbox overlaps with the obstacle's hitbox, subtract 10 health points, play a damage sound effect, and trigger a brief invincibility frame. That precise conditional logic, that's your algorithmic design. The third pillar here is decomposition, which makes problem-solving way easier by focusing on individual, bite-sized pieces. We don't just tackle a massive problem all at once. No way. We break it down, write code for those smaller parts, and then test them independently. For new coder, decomposition is honestly the ultimate psychological benefit. It effectively cures that dreaded blank page syndrome. When you decompose a project, you're transforming this impossible, insurmountable mountain into a series of highly achievable, practical stepping stones. And finally, pattern recognition. This is what allows us to avoid reinventing the wheel by applying known solutions to similar subproblems. By spotting recurring similarities within data or software architectures, we can use existing heavily tested code to drastically speed up our development time. Here's a pretty cool fact. Almost every modern game you play reuses the exact same pathfinding algorithms, like the famous A-star search algorithm, to dictate how enemies move around a map. Developers recognized the pattern of map navigation ages ago, solved it, and now we all just reuse that brilliantly efficient solution. Moving right along to part 2, abstraction, and how we go about hiding the complexity. The classic car analogy perfectly illustrates this concept. Just think about it. You don't need to understand the insanely complex mechanics of an internal combustion engine to drive your car down the street. The steering wheel and pedals act as your abstraction layer. They provide a really simple, easy-to-use interface between you, the driver, and the underlying mechanical processes. Imagine how completely paralyzed we'd be if we had to mentally calculate exact fuel injection ratios and manually adjust transmission gears every single time we just wanted to parallel park. Well, in coding, abstraction prevents that exact kind of cognitive paralysis. Similarly, think about something as everyday as moving your computer mouse. You are completely abstracted away from the wildly complex logic happening under the hood. I mean, physical sensors detect the motion, an internal processor formats that into data packets, the hardware shoots an interrupt signal to your CPU, and the OS calculates the new cursor position. But you just see the little arrow move. For student coders, think about how this applies to mobile joystick logic. A player dragging their thumb across a glass screen is triggering an incredibly complex series of touch-capacitive hardware interrupts. But thanks to abstraction, the game engine decomposes those complex touch inputs into just two simple variables, an x-coordinate and a y-coordinate. You don't have to code the physical electrical changes of the glass screen, you just write simple logic for x and y. It's a lifesaver. That brings us to part 3, decomposition, or breaking problems down. So, decomposition gives us this highly visible thinking routine that acts as a practical toolkit for literally any project. First, identify the complex whole you're trying to build. Second, list every single component that makes up that whole. Third, describe the specific function of each individual component. And fourth, map out how they interconnect. For instance, if the whole is a health system, your components are the health bar interface, the player's maximum health variable, and the damage calculator. Their functions handle displaying the color red, tracking the numbers, and subtracting damage. Finally, you map them out so the damage calculator automatically updates that visual interface. It really is a systematic, foolproof approach. Now, if you get stuck during this process, I highly recommend trying the Explain Like I'm 5 method. It's incredibly effective because it totally forces you to strip away the jargon, remove those complex dependencies, and find the absolute simplest logical units. Like if you're trying to code a stealth mechanic and getting completely lost in the weeds, this method forces you to just say, when the enemy looks at me and I am not hiding behind a box, the alarm rings. Boom, you just isolated 3 independent parts: enemy vision, a box collision check, and an alarm state. That right there is the power of extreme simplification. All right, let's look at a practical application in part 4, our case study on game development. Applying this directly to game development reveals how a highly complex non-playable character, or NPC, is actually decomposed into just 4 simple programmatic variables. Instead of trying to code an entire seemingly intelligent enemy all at once, we just break it down. We give it sensing, which is really just code looking for player proximity. We give it decision-making, acting as a behavior tree to evaluate situations. We code actions, like playing a specific attack animation, and pathfinding to navigate the environment. This fundamental logic creates deeply effective and engaging player experiences. The player feels like they're fighting a living, intelligent creature. But the coder? The coder knows it's fundamentally just 4 simple decomposed scripts talking to each other. Zooming out to the bigger picture, mapping relationships visually separates the entire game into independent objects. Imagine a Pac-Man clone. We separate it into a map class, a player class, and a ghost class, and all of these feed into the main game class. This object-oriented approach makes the coding process incredibly organized. You aren't coding the whole game at once. You're just coding a single ghost, testing its behavior, and then moving on to the next thing. Visual relationship diagrams act as the ultimate map for simplifying complex control concepts, especially when you have a whole team working together. This structured approach is exactly how massive studios coordinate hundreds of developers without everyone constantly stepping on each other's toes. And finally, part 5, putting it all together. When you enforce the single responsibility principle on these decomposed parts, meaning every single piece of code only has one very specific job to do, your software becomes infinitely easier to test. Honestly, this is where all your hard work pays off. Because each module is independent, multiple programmers can work concurrently on entirely different features without breaking each other's code. You can even reuse generalized code across totally different projects. When every puzzle piece only has one job, bugs are instantly isolated, testing is remarkably easy, and building the machine actually becomes a joy rather than a stressful nightmare. Eventually, you synthesize the solution, rebuilding the complex whole, piece by perfect piece. Understanding abstraction and decomposition completely changes how you view technology. The magic of software, well, it isn't magic at all. It's just masterfully organized logic. So I'll leave you with this. The next time you open your favorite app or game, don't just passively consume it. Challenge yourself. Ask, what are the basic computational steps hidden beneath the glass? How would you decompose it?